Hello everybody. So what we're looking at today is related rates. So related rates, very complicated. What it is about is it's about rates that are related. Question mark? No question mark. Yeah, that's what it's about. Rates that are related. And so the basic idea is actually pretty simple, really. So that's easy. That's good. What's difficult about them or challenging is that they're generally word problems. If you're lucky, they make it very straightforward, and if you're less lucky, then it's a little bit trickier. So we'll see some of both kinds. So here's the idea, though, for the math. Here's the math that you need to know. So you learned the chain rule, right, in the previous lecture. So now you know the chain rule in the last lecture. And we learned it this way. We learned that when you do the derivative of a function, you get, let's see, you take the derivatives of the outside first and then the inside. So you go f prime g, g prime x. Okay, but we can apply that in a slightly different way. So let's say we have this. Consider this. So mostly I'm just changing the letters here, but that's not all I'm doing. So I'm going to take the derivative with respect to t of a function of, it could be any variable. I'm just going to go with x, f of x. Okay, so ddt of f of x. And so the key here is to notice that the derivative is with respect to one variable, but the variable in the function is actually a different letter, right? So different letters, right? So the derivative is with respect to a different variable. Right? So what you have to do is you treat, so this is the key here, you treat the x that you see in there as if it was actually x of t, right? Like if x was a function. So x is a function of t, right? So what that means is, like, I wrote it the way I wrote it, but I could say the derivative of f of x of t. And in that case, you would, think about numbering these functions 1, 2, and then I guess 3, but you don't need to write it because that one matches the variable. And then you take the derivatives from the inside out. So it would have to be f prime of x. I'm not going to write the of t there. So f prime of x times x prime of t. We don't really like to write it that way, though. You'd probably see it this way. F prime of x. And then instead of x prime of t, you'd probably see dx dt, which you haven't been using that form of the derivative very often, but in this lecture you're going to see it a lot because they want you to see that it's a derivative with respect to t. Okay? Now what does that mean? What are the implications of this? Basically, that should not be capitalized, but it is. So basically, all of your derivatives in this section are with respect to t. and you'll do them like this. That doesn't say this. Do them like this. So here's some examples of how they're going to work. So you're going to get something like this. So let's say I say, I don't know. Well, I do know. But let's say I have area, or forget area. A equals 4x squared plus y. Right? So I have just a mix of variables, right? Mix of variables. Now, you're going to apply the derivative. So, apply d dt. Why t? Because what I said right up there. All the derivatives in this section are with respect to t. So we're always going to be doing those. So we're going to go d dt of the left side and d dt of the right side. Okay. When you do those derivatives, you're going to be paying attention to the rules for the chain rule. So again, look at what we do, right? The key here is to notice when you take the derivative of a function of x now with respect to t, you just do the derivative normally, right? F prime of x. And all you're going to do is throw a dx dt on the end, right? That's it. Just throw a dx dt on the end. So whenever you do one of these derivatives, you would just say like, okay, well, what would the derivative, if a was a variable, what would the derivative of a be? It would be 1, right? Like the derivative of x is 1. But then for that chain rule part, you multiply by dA dt. And then over here, you say, well, the derivative of 4x squared. What would the derivative of 4x squared be? It would be 8x. So you write 8x, but you put a dx dt on the end, right? Dx dt, because x was the variable there. Then you have y. What's the derivative of y? Well, the derivative of y with respect to y is 1. But then you add a dy dt. Right? So you do those derivatives as if you were taking the derivative of, you do all the derivatives as if you were doing the derivative normally with respect to that variable, but then you throw dA dt, dx dt, dy dt, whatever it is, based on the variable that you just took the derivative of. So let's look at a different one. Another one. Let's do another example. Let's say d dt, they're all d dt of, let's say, what do I want? V squared equals, and this is like, made up, it doesn't mean anything here. X squared y squared. Oh, oops, I don't want that. So let's say we have that. And I take the derivative. So I apply the derivative to both sides. So d dt v squared equals d dt x squared y squared. All right? Then what you're going to do is you should notice that you have a product here, right? X squared y squared. And we're treating every letter like it's a variable. So that means if we have a product, we need the product rule. So you still have to use all your rules. It's generally not going to be one, or if there is, it'll be product rule. Shouldn't be too bad. So we're going to do the product rule there. So let's take the derivative. On the left, the derivative of v squared should be 2v, but dv dt. On the left, it's going to take us 2 lines. It's product rule, so like f prime g plus f g prime. Now be careful with the primes. Remember that the primes are d dt derivatives this time. So that doesn't go away just because I wrote a prime. So the derivative of x squared is 2x, but I just took the derivative of an x function, so dx dt, and then y squared. There's no dy dt here because the part that I was taking the derivative of was an x variable, not a y variable. Right? There's a y, but I wasn't taking the derivative of it. So you don't add a dy dt unless you just took the derivative of a y. All right, over here. X squared, no derivative, so we're just writing x squared. And then you need the derivative of y squared. That's going to be 2y dy dt. So you get this. 2v dv dt, 2x dx dt y squared, x squared 2y dy dt. And that would be your derivative, right? So they just all have this extra thing tacked on, but you only add it right when you take the derivative of a variable, of a function with a particular variable in it. So it only appears on that last line there. Well, this one was up here. But when you take the derivative, that's when it happens. Okay? And that's all the math that you need. And it is really just the chain rule. Okay? The next thing you need to know about this is every d variable dt is a rate of change, right? Remember when we talked about average rates of change and that kind of thing? Every d whatever is a rate of change. So like, for example, dx dt is the rate of change of x with respect to t, which is time. Okay, so dx dt is the rate of change of x with respect to t. Like dv dt is the rate of change of, maybe that's v, maybe that's volume, with respect to t, which is probably time, right? And so on. So every dx dt or anything dt is a rate of change. And so when we say related rates, we're talking about derivatives being related. And so if you look at what we did on our examples here, right? Like let's just look at this. This is a rate. This is a rate. This is a rate. So there's 3 rates in that problem, and they're all in the same equation, and that's why they're related. So the rates are related. How are they related? Well, they're in an equation together, and the equation is how they're related. So that's why this section is called related rates. So what you're going to be doing is you're going to be writing an equation like this, basically, and then all you're going to be doing is plugging in numbers for everything except 1, and whatever you don't plug in a number for is what you're trying to solve for. Okay, so these are all word problems. So these are word problems. And the way you're going to solve them is going to be something like this. You're going to draw a picture if you don't have one. A lot of times they give you one. Draw a picture of what's going on. In your picture, make sure you label anything that might change with a variable. All right. Now, before we take a derivative, well, we got 2 things to do here. one thing we're going to do is label anything that changes with a variable. You also need to write an equation that relates your variables. Now those are should be easy. When I say it should be easy, like if your picture is a circle with a radius, right, and they're talking about area, then your equation is like area equals pi r squared, because that's the area of a circle. Or if it's a complicated picture, they just tell you what it is. You know, if it's a rectangle, maybe it's area equals length times width or something. Okay, so that's not supposed to be too hard, but you write an equation that relates your variables. At some point you need to do this, so I'm going to do it right here. I'm going to say make sure you write out all known numbers, you know, in terms of what variable they are. All right. And then your equation from 3, you're going to take the derivative of. So apply d dt, right, take the derivative, to the equation from 3. Then you're going to substitute in all the numbers you know, and solve for whatever's missing. You know, the one that you need for your answer. Right? And some of these you can do out of order. Like you can write down all the numbers that you know and stuff before step 4. But basically this is what you're going to do. Let's see if we can do one. Okay, yeah, so here's a very basic one. A square has a side length that is decreasing at a rate of 8 cm per second. What is the rate of change of the area of the square when the sides are 7 centimeters. Okay, so this is a related rates problem, right? They're like literally talking about rates. So yes. So what's the idea here? I think I can draw the picture right here. So the idea is pretty simple, I think. You have a square. If I could connect the lines. That's not a square. I made it the wrong number of boxes. All right, 4 by 4. 4, 4, 4, 4. Make it 4. Okay. There's a square. Okay. Now, all right. I drew a square. What's next? Label anything that changes with a variable. Okay. So what's changing? They say a square has a side length that is decreasing. So the side lengths are decreasing. So what I need to label it with a variable. Easiest variable to use is just x, right? It's x by x. Now I know it's the same because it's a square, right? Squares have length and height, or length and width the same. What else changes? What is the rate of change of the area of the square? Well, I don't really know where to label area, but I mean, I'll put it on the inside and I'll just call it A, right? Okay, that's it, right? It's a square. Area is A, sides are X, the end. Write down an equation relating your variables. variables. All right, so my variables are area and x. So our equation, right, we're on step 3. What's the equation that relates the area to the x? Well, it's a square. So the area is x squared, right? X times x, length times width. That's all. I'm gonna write length times width, right? That's all we're doing there. We're just writing a and x. We're just writing a equals x squared. That's the equation that relates a and x. The next thing we were supposed to do is I said we need to write down what we know. And so the idea here is if we have a and x, there's actually 4 things we can talk about. We can talk about x. We can talk about a. We can also talk about dx dt. And we can also talk about dA dt. So whatever the variables are, you have the variables, but you also have the derivatives. So you have double the number of things as you might think. Okay? Now, those are the things that we could know. We need to know what are they at the time we're talking about. So at the moment we care, right? Because it's always changing, but at the moment we care about it, we know, and this is where you just look to read the numbers out of here. So they say that the sides are 7 centimeters. So if the sides are 7 centimeters, what's that mean? That means x is 7, right? So sides are 7 implies x equals 7. We know that. Also, though, before we move on from that, they don't tell us what a is, but if you knew that it was 7 by 7, right? So the sides are 7, that means x is 7, but also, what's the area when the sides are 7? 7 squared, right? So 49. So this is 7 cm, and then this is 49 cm squared. So they didn't tell you that one directly, but you were supposed to know it from the fact that the sides were 7. What else do we know? A square has a side length that is decreasing at a rate of 8 cm per second. So when they give you a rate, they're telling you a derivative. So sides are 7, x is 7, but also a is 49. But then they say rate of sides is negative 8 cm per second. Why negative? Because they said it was decreasing. Decreasing, so it's going down. So it needs to be negative. So the rate of the sides is negative 8 cm per second. But what's a side? A side is x, so that's actually dx dt is negative 8. Again, cm per second. So you put that here. Negative 8 cm per second. So we know most of these now. We know x. We know the area because it's just x squared. They told us the rate of change of x. What they did not tell us was the rate of change of the area. Right? This is the only one that we're missing. Only missing dA dt, which is the rate of change of area with respect to time. Which I'll write t. So do you see how this works? You write out everything you know, and you're going to be missing one thing, and then you find it. Now, I should caution you, though, sometimes you're missing more than one thing, and it doesn't matter that you're missing it. So if you're missing 2 things, maybe you just don't need it in your equation, and then it's fine. All right, 5. Apply ddt to your equation. So step 5, where's my equation? A equals x squared. So we apply our derivative, 5, ddt a equals ddt x squared. So the derivative of a is 1, dA dt. The derivative of x squared is 2x, but then dx dt. So that's it. That's all you're doing there. The derivative is easy on these. The hard part is the word problem. Then what? Substitute all the numbers you know and solve for the one that you need, right? So step 6. Sub in the numbers. Now, you can and maybe should write in the units for every number that you plug in, but nothing happens if you don't. Like it should still work out. So dA dt we don't have a number for. But we have 2x. What's x? 7 cm. And we have dx dt. What's dx dt? Negative 8 cm per second. And then we'll just multiply that out. So 2 times 7 times negative 8. So 7 times 8 is 56. 56 times 2 is that 112? I feel like that's 112. But, you know, math is hard. So I'm doing it on a calculator. 112. So dA dt is negative 112. And then if you look at the units, you have a cm and cm over seconds. That's cm squared over seconds. And if you think about it, square centimeters per second is a rate for area. So the units just worked out like they should. All right, that's it. So that's a whole one of these problems. Notice that all of the actual like calculus is right here on the page right now, and it's a very small amount of calculus, right? What's hard about these problems is all the stuff you have to do ahead of time, like drawing the picture and coming up with the equation and so on. And that's how they are, though, okay? And that's a related rates problem. Why are they related rates? Because right here, there are some rates that are related. Rates are derivatives. All right. Also, I noticed on the homework, by the way, that you don't write in the units. So keep that in mind. Okay. Something else that's true about this section is they really like triangles, like really like triangles. So here's one. Triangle has a base that is decreasing at a rate of 10 feet per hour. Sure, why not? With the height held constant. I don't know what that means. What is the rate of change of the area of the triangle if height is 6 feet? Okay. Yeah. So they didn't really tell us what the triangle looks like. I don't know if the triangle is like this. Like, I don't know, like, should we draw a right triangle or should it be like this? Should be like this. None of it matters though, because it doesn't matter what picture you use, because they told us base and height, and you know that for a triangle, the area is 1/2 base times height. So it doesn't matter what the exact triangle looks like as long as it has a base and a height that you can write down. So it doesn't matter. So, you know, it doesn't matter what the drawing looks like on this one. So you don't have to think very hard about it. We're just going to draw a triangle. So let's draw a triangle. Not that one. Better triangle. Okay, so there's my triangle. This is the one I'm going to use. And so there's my picture. Now I'm supposed to label variables on it. So I've got a base, and the base changes. All right? And then I've got a height. So if I draw in the height here, there you go. Now you actually have a choice here. You could label the height as h for height. All right? But you don't have to, because they tell me that the height is held constant, right? If they say the height is held constant, and then they say that the height is yeah. Wait a second. Oh, okay. Yeah. I was thinking that we didn't have enough information based on what they told us. But because notice that they told us the rate for the base is 10 feet per hour, but they didn't actually tell us what the base was in terms of a length. Turns out it's not going to matter, or we're not going to need it. But that's weird that they didn't tell us. All right, what is the rate of change if the height is 6 feet? But the thing is, height is constant. Height is constant, so you don't have to put in an h because it's not changing. You only need a variable if it changes. So if the height is constant 6 feet, put in 6. Just draw this picture, right? Because the 6 for the height is not changing. So we do that. What's step 2? Oh, that was step 2. Write the equation. So the equation, keep scrolling. So the equation here is going to be, I guess we're on step 3. We're talking about areas of triangles. So area is 1/2 base times height in general, right? But for us, the height is fixed. So I'm just going to say 1/2 base times 6, or rather area is 3b. Now again, you could have left it in h, but it makes the derivative harder in the next step. So that's why I did not. We knew it was 6, so put in 6 right now. But you can only do that if it's not changing. All right, step 4. Write out all the numbers in terms of what variables they are. Like what do we know are about numbers? So at the time we care about, there's only 2 variables, right? There's no h because h is fixed. So there's only a and b. So there's a b, a db dt, then there's an a, and then there's a dA dt, right? Those are the 4 we got. Now, what do we know? Well, they didn't tell us any of these, right? They didn't, like, the only thing they told us was the base. They told us that the base was decreasing at a rate of 10 feet per hour. So the base, they told us the rate for the base. So the rate for the base is 10 and it's going down. So where's that? Here, -10 feet per hour. And look though, they didn't tell us the base, they didn't tell us the area. We can't even calculate them, right? Like you can't calculate this without knowing, like you could, if you knew the base, you could calculate the area. If you knew the area, you could calculate the base, but they didn't tell you anything. So actually, you know, we don't know any of those. Kind of weird that we don't know that many, but that's how it is. That's what they told us. What's step 5 or 4? No, 5. Apply ddt to the equation. Right? That's the wrong green. Okay. 5? Is that 5? apply d dt. To equation. So what's the equation? The equation is area equals 1/2. No, it isn't. The area is area equals 3b. So we're applying d dt. I didn't leave room. I don't know why. So put a d dt there. Put a d dt there. All right. What are we going to get? Well, d dt of a is 1 dA dt. d dt of 3b is going to be 3 dB dt. All right? And if you actually look at this equation, you can notice that it's actually, there is no a and b in it, right? Like, look at that. It's just dA dt and dB dt. No a, no b. And so back up here where we don't know a and b, turns out it doesn't matter. We didn't need them. So step 6, sub in numbers and solve for what you want. Which, what do we want? What were we looking for actually? So, I mean, do we know? I think we know. They told us what we're looking for. What is the rate of change of the area of the triangle? So they want this. This is what we want, right? This is the one we want. Okay. All right, so what do we have? We have dA dt equals 3 dB dt, but they told us dB dt is -10 feet per hour. So what is it? -30 feet per hour. It must be feet squared. Oh, because the 3 was, I didn't write the units, but remember that this was 6 feet, so there was really feet on there. So actually that should have been 3 feet. 3 feet, and then here 30 feet squared per hour. You don't need the units for the answer on Newton, but for yourself you should know them. All right, so -30, that's the answer. And so really you're just doing this you know, a bunch of times. Yeah, you're just doing this a bunch of times. So let's see here. Do another one? Yeah, let's do another one. So as we do these, we should be getting a little bit faster as we become more comfortable with the method. So sometimes, you know, you're not even going to have a good idea of what the picture is. But this one's complicated. An inverted cone, already confused. Cone has height 11 inches and initial radius 18 inches. Okay. The volume of the cone is decreasing. How is that happening? At a rate of 541 cubic inches. I started to write centimeters. Cubic inches per second with height constant. What is the rate of change of the radius when the radius is 5 inches? All right. Now this definitely sounds like the most complicated one that we've done. It is the most complicated one we've done, but you know, in terms of the math, it's not going to be that much worse. It's just understanding what's going on. So an inverted cone, that's, I don't know if I can draw an oval. Oh, I can. Cool. So an inverted cone is like this. Mine's lopsided, but I'm not fixing it. And they told you that it has a height of 11 inches. Come on. And then they say initial radius of 18. Okay, but somehow over time, I have no idea how this is happening, but somehow over time it must be getting skinnier because somehow over time it must be getting skinnier because it's staying 11 inches, but then the radius is shrinking somehow. So I don't know how that's happening. I do not know how that's happening, but that's what they're claiming is happening. That the height is staying 11 inches, but the cone is shrinking somehow, right? So we don't care why that's happening. How in physics would that be happening? But it is happening. So luckily for us, here's what they tell us. They say V is 1/3 pi r squared h. So they're nice enough to give us the equation. So this is just given as the equation. So when they give you a complicated shape, they just tell you the volume of it, so you don't have to go look up the volume of a cone. All right? So that was given to us as the equation. So what are we going to do with it? Well, we are going to, what step are we on? We do the picture. I think we actually even labeled the variables, right? Actually, I mean, we didn't label the height, but height, right? So we label them. They're H and R. Those are our variables. They gave them to us here. I didn't label volume, but it's volume, V, okay. We have the equation. So if we already have the equation, we're already on step 4. Write out what we know in terms of the numbers. So at the time we care about, I'll write that in pink. What are the variables? There's V, R, and H. So there's V, there's R, there's H, and then there's dV dt, dr dt, and dH dt. And then we fill them all in. So at the time we care about, what do we know? At the time we care about, the radius is 5 inches. Okay, good. At the time we care about, the height is 11. How do I know it's 11? What did they say about it? Height is constant, right? Height held constant. So I know H is 11. Actually, there's one other thing I know. If H is 11 as a constant, then the derivative of H is 0, because rate of change, dH dt is rate of change, and if H is constant, the rate is 0. H is constant, it says his, H is constant, so rate is 0. That's something that you should know for filling these out. What else do we know? Volume of the cone is decreasing at 541 cubic inches per second. So that's volume decreasing. So that's the rate for the volume. It's decreasing, so it's negative. So negative 541 here. Right? And you can write, if you want units, inches, cubic inches per second, maybe? Yeah. All right. Dr dt, did they tell us dr dt? They did not. What do they want? Oh, what is the rate of change of the radius when the radius is 5? So they actually this is the one that they want, right? That's the one we want. So we're missing the volume, right? Now, I could calculate the volume because I have this equation right here and I know R and H, so I could calculate the volume. I'm not calculating the volume because look where it is in the equation. When we take the derivative of V, it's going to be dV dt, right? So we're not going to need the volume in the equation later on. So even though I know how to calculate the volume, I'm just leaving it blank because I'm lazy. All right. Now we need to take derivative. So I've got V equals, I'll put it, ddt V equals ddt 1/3 pi r squared h. Okay, take your derivative. Now, on the left it's just dv dt. Like I said, we're not going to need v, so that's nice. On the right though, you've got the r's and the h's. You're going to have to do the product rule. So just treat all of this as your f for the product rule, and then treat the h as your g for the product rule. You actually don't have to technically do that because h is constant, but we'll just do it with the product rule. Product rule. So that's okay. F prime g plus f g prime. All right, so we take our derivatives now. So the derivative is going to be 1/3 pi, and then the derivative of r squared is 2r, but you tack on a dr dt, and you have an h. Plus 1/3 pi r squared. The derivative of h, that's ddt of h, is dh dt, or 1 dh dt. So there's my derivative. Then we plug in our numbers, and we'll see what we get. So we put all our numbers in here. So we've got the change in volume was negative 541. I'm not going to write the units. Then we have 1/3 pi times 2. I could have moved that to the front. R, what's R? 5. What's dr dt? We don't know it. What's h? 11 plus 1/3 pi r, what's r? 5 squared. What's dh dt? 0. Right? So it turns out that because h is 0, you don't need this. Because dh dt is 0, that whole thing's going to go away. So what we have is negative 541 equals, multiply this all out. So I've got 2 times 5 is 10 times 11 is 110. 110 over 3 pi dr dt, if I did that right. So dr dt, which is what we're solving for, you're going to have to move all this to the other side. So you have negative 541 times 3 over 110 pi. And if you work out the units, I guarantee you would work out. So we're going to have, let's see, 541 times 3 over 110. Can I get that as a fraction? Okay. Exact answer, they say. All right, so exact answer means we got to leave the pi as a pi. All right, there it is. That's 1623 over 110 pi, if I did it right. And let's see, 1623 over 110 pi. Submit. Uh-oh. Oh, I forgot the negative. Ha 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 ha. Okay, now it's right. All right. So I'm out of time, but I think we did a lot of these. come to office hours if you have questions about it. I will see you then. How do I